crystal parts, and the differentiation of a crystallographic axis and axial ratios, those are also you need to identify, and discuss the crystal parameters and crystallographic notations. These must you have to identify after completion of these course in theory and as well in the practical class. So there are some elements are there in a crystal. Now we see the crystal formation. What are the habits and the formation of a crystal? We see here. The crystal habit we can define in a general aspect. Definitely, it has a shape, and which is a processes produced by the relative development of different forms. And the habit it is used to denote the general shapes of a crystal, such as maybe it is looking as a cubic, octahedral, or maybe sometimes we see those crystals in a prismatic structure or a shape. So depend on their environmental, at the time of the crystallization of environment conditions. So different crystals are having a different structure, and depend on their at the time of a temperature and the pressure, the crystallization will be done. So that uh, according to that the crystals are formed in a different structure. So we see that here the crystal form also. How we can define the crystal form? The crystal form we see it is a assemblage of a crystal faces, and it is related to the each other by the symmetry that crystal possesses. We'll use here Miller index. The Miller index it is defining the. It is useful to define the crystal form. The crystal how it was formed. Maybe it was formed by the solidification from the different gases, or sometimes we see that those crystals it is formed from the liquid state, or sometimes maybe it is a precipitation of some solutions. So according to that, the complete overall the process will be done in a crystallization. So that here the crystals are a solid geometric figures which are bounded by the well-developed more or less plane surfaces called here the faces. You see here, just you can see here it is a quartz crystal. It is known. It is looking as a quartz crystal. You see, it is the flat area. The flat area, the surface. It has a plane, but sometimes maybe it is acting. It is having the uh, more plane, or sometimes maybe some of the crystals are having the less plane. So this phase, it is this is known the plane area. It is the plane. It has surface. The surface it has a plane. Maybe it has a low plane or more plane area. The surface it is known as the phase. This one is. So it is a quartz crystal. What I'm showing here, it is a quartz crystal. These two are the quartz crystals. How you give the perfect definition to this? Yes, there are some internal arrangements of atoms which defines whether are substance or not substance in a crystalline. The conditions are favorable for this solid bodies which become bounded by the smooth surface. In this way, they assume the regular geometric forms are known as crystals. So crystals can be defined homogeneous material and solid bounded material, and which is formed naturally, and it has a plane surface, and definitely it has a chemical composition. That's also important here. So it has some characteristics. What are those characteristics we see? Crystal, it is a regular polyhedral form, and it is characterized by the flat surface. It is known as a face. It is known as a face. You see here that. Suppose maybe if it is, you feel it is a crystal model, it is I'm showing you here. This is a crystal model. You see the plane surface it has. The top one, it is a plane surface. So the plane surface, it is known as a face. Face. Yeah, again, which is formed with using of internal atomic structure. Definitely, it has an internal atomic structure. The internal atomic structure. Once I'll show you one more. You'll see here. The internal atoms. These are the internal atoms. These are internal atoms, and the space it is provided between these atoms. See here, the space it is providing, and internally it is connecting to the one atom to the another atom. You see here is this one. It is connecting to this. Systematically, the atoms will arrange. So this is the connection. It is known as a bond from one atom to the another atom. So slowly it is forming on the basis of a lattice and the crystal structure which is forming combination of the two. One it is a basic basis and second one it is a lattice. It's a linear of lattice and the plane surface of this lattice, and lattice it has a different atoms. The combination of the two lattice and basis, and those will lead to formation of a crystal. So here crystal axis is also there. The crystal axis also, which is playing very important role, and crystalline substances. We need to know the crystalline substances also. The crystalline substances, definitely it has a, yeah, the crystalline substance definitely it has a solid formation. It has a solid formation, and it has polyhedral structure. Yeah, polyhedral structure. Okay, here it is showing that the models, whether it's glass or model and wooden models also. I'm showing you here. Definitely, it is a required atomic structure. Whatever you are making here internally, it is mm, made up of atoms. Without atoms, there is no chance at all to formation of these uh, crystal. Okay, how do we study the crystallography? How we can study the crystallography? The crystal, we know that it is a homogeneous anisotropic solid material, and it has a definite chemical composition, and it should be formed naturally, and it has an inorganic composition. So finally, these properties, the combination of these properties, it is known as a crystal. The study of a crystals, the science, it is known as a crystallography. The person who is studying that is known as a crystallographer. Crystallographer. Okay, as of that different rocks are there. These different rocks are aggregating of different minerals. So how? The based on this, we'll consider the rocks we can see in a Earth's crust. The minerals also, whether sometimes maybe it is amorphous or sometimes maybe a crystalline. Anyway, these all formed by the natural compositions of different elements. So here how we can study that? We can study that with the using of a X-ray, X-rays of crystal study. The internal structure and internal characteristics of the crystals we see with or we'll study with the using of X-rays. So the first time in 1913, the first structural analysis of crystal of a sodium chloride was done by the Sir W.H. Bragg and Sir W.L. Bragg, two English physicists. And they got a Nobel Prize in 1915 based on this work, and they have introduced one principle for studying of this one, the structures of NaCl, zinc sulfide, and diamond also. Diamond also with using of this principle, that is n lambda is equal to d sine theta. And it is an integer. Lambda, it is a wavelength of an incident X-ray beam. The d, it is known as the distance between the atomic layers in a particular crystal what we are going to study. So based on this principle, we'll study what are the minerals are there and the arrangement of the crystals in that. So here we see that again the next one, it is the parts of a crystal. Every um, substance or every material, it has some parts. So what are those in a crystal point of view we see here? One, it is that the phases. The phase means it is a plane surface of a crystal. Plane surface or plateau surface. You see here, this is one, and this is also phase, and this is also phase, and the bottom, this is also phase, and this top, I mean the side one, this also phase, and this is also phase. You see the flat surface, it has a flat surface, and which the crystals are bounded with them. It is known as a phase. Okay, the phases are almost parallel to the net planes in a crystal structure, 100%. Definitely. It's a parallel to the plane surfaces. Whatever it is that you see here, and in previous picture, this also you can see here, this is known as a face, and this side also you can see here is a glass or whatever it is that the model you can see here, the top flat flat surface, it is known as a plane surface, it is known as a face. So here sometimes the crystals we see the flat, sometimes maybe they are curved. Example for you see in some minerals for siderite, dolomite, and diamond. Or some of the crystals are so similar. The crystals are like it is like faces. Example for that, galena. Or some of the faces are not like a plateau. I mean flat areas. Those some are having the flat areas, some are having the not flat areas. So here we divided those faces depend on that like faces or unlike faces. Okay. Yeah. Yeah. Again, the differences may be slightly differences we see according to their physical properties. So here the size and the shape, that's also playing the very size. It's also playing the very important the formation of crystal face. So here there are six faces we see in a cube. That's a example for a galena mineral. Galena mineral, sorry. Yeah, this is about face, and Here given the picture, you see the first one, it is a cube. It is showing the single form. This one single form. Almost we will look into the it's a some square shape or rectangular shape. So plateau areas we see. This is known as a single form of a crystal. And whereas you can see into the second picture, these are not equal faces which are having. It is known as a unlike faces. Here, triangular shape we can see here. It is looking as a triangular shape. The top and the bottom, but between these two bottom and the top, the space it is looking as almost rectangular shape we see here. Compared with one, this one, and this one, the rectangular and triangular face, both if you can compare, both are having the different faces. So these two are known as a unlike face. But here in a top portion, you see here, this is the side, the this side and this side, these two are looking into the like faces. And here also we can compare with this one in a B picture, and this one we see that is known as a unlike faces. Depend on their combination. The combination sometimes maybe the combination of like faces and unlike faces, these two, which is leads to formation of crystal. So the next one it is edge. Yes, this line it is. You see here one face, and this is a one face, and this is a one face. There are two faces will be joined here. It is intersecting the adjacent faces. You see, this is one face and this is one face. The line it is indicating. It is intersecting or joining, whatever we will call. The joining of two faces. The joining of two faces. The line it is indicating, this is known as a edge. It is known as a edge. So naturally it has a straight line or a straight position on a crystal and a crystal. And yeah, so next one it is the edge. Sorry for the interruption. Yeah. These two faces will be joining, and it is creating a one line. It is creating a one line, and the line sometimes maybe it is intersecting of two faces also. The line it is known as a edge. This is the edge, and this is also you can see here. This is also edge. This one face, and this is one face, and the outside or that side of the portion it is also the plane surface it has. So both combination of two surfaces. The line it is a the straight line it is indicating as a edge. This is one thing, and yeah, the solid angle it will be creating the solid angle where it is creating the solid angle. You see here the solid angles which are formed, the intersecting of three or more than faces. You see, this is one face, and this is one face, and the this side also you can see the outside also we can see one face. Or else you can see this is the best example. One, two, three, four, four faces. In a four faces, just you can see here, it is creating this one, this creating as an angle. Here it is showing. Here one face and this is one face and the outside, that side of that, and where it is that the meeting, you see here the edge, it is known as the edge, it is this here, the corner place, it is known as the solid angle, it is creating that solid angle. So here there is a principle for this one. So F is equal, F plus C is equal to E plus 2. Okay, if you can abbreviate this one, yep, it's a number of faces. This one, number of faces. C, it is known as a number of solid angles. C is known as a solid angles. This is example for this one. This is angle, and this is angle, and this is angle. And we will call this is known as sometimes in corners also. It is known as corners also. Here. So E, it is number of edges. This one, the edges. This number of edges. So finally, the principle it is known that F plus C is equal to F plus C is equal to E plus 2. E plus 2. So now we see that formula example for if you are taking that cube. Cube, how many faces it has? Suppose if you feel this is a cube actually, you see here how many faces? This one, two, three. Same, this is also having this side one, two, three, back side. So three faces, 3 plus 3, 6 faces we see here. F is equal to 6. And number of solid angles. Here it is creating the angles. How many angles it is creating? 1, 2, 3, 4, 5, 6, 7, 8. 8 angles it is creating. So that C is equal to 8 solid angles is creating. Uh, Solid angles are creating. And later, number of edges you see here. The number of edges here, what is the edge? This is one edge. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges are created. So that now we see that number of edges are 12. Now you put these values you into this formula. F is equal to 6. 6 plus 8. This is C is equal to 8. C is equal to 8. And then is equal to 12. This is E is equal to 12. And 2. The principal will add 2. So here almost we will get equivalent. 8 plus 6, 14 is equal to, and 12 plus 2 is equal to 14. So the value it should be equal. The value it should be equal of the angle. So if you are not getting the correct, if it is not unequal, maybe something it is there. So in further you will get about that. Okay, Jones and the axis, Jones axis. The study of the crystals are shown in many crystals. The faces which are arranged in a manner in the different edges which are formed, and those are intersecting of faces parallel to one to another. So that such set of edges belongs to the group of faces. The group of faces are there. So here, uh, face whose mutual intersecting gives rise parallel edges, which defines as a zone. Okay, you see here, uh, this one. You see the face, it is similar to the zone, similar formation, similar form which are having. So this is one zone, and this is also forming a zone, and this is also forming a zone. And here internally the C axis, which is passing through all these axes, and where all these axes means where they are going to meet in a edge or in a solid angle. Through this is a solid angle, but not edge. This is edge, and all the edges were connecting here, and here also you can see here. And through this line or through this axis, sorry, through this edges or through this solid angle, the axis will be passing. That is known as a zone axis. It is known as a zone axis. So here, internal angles also there, or the that is known as a interfacial angle. See here the interfacial angle, if we can define that, the angle between the two adjacent faces of a crystal. You see, this is a face and this is a face. In a crystal, I'll show you. This is one face and this is one face. You see, it is creating the face and this is also creating the face. You see, this is one face and this is one face. So now complete it. Between this angle, it is creating some angle. The angle, it is known as a interfacial angle. It is known as a interfacial angle. Simply, this is one face between the two faces, or any two faces. The adjacent two faces, that should be adjacent two faces. Between these two faces, the 90 degrees of angle. You see here, this is one line and exactly the 90 degrees of position. And from this face, this is also creating the 90 degrees of angle where they are going to intersecting. Somewhere it is intersecting. The intersecting point, the angle, it is known as the interfacial angle. Interfacial angle. So it is useful for to arrangement of a crystals in a mirror, to find out the arrangement of crystals. Every the mineral, it is made up of a different crystals. So that in that mineral, which crystal was arranged in which direction. Based on this, we will identify that the crystal angle with using of this. So that is one thing. And second one, it is there is a meter for that. There is a that is known as a goniometer. It is useful for to find out the interfacial angles. How we can measure the interfacial angles? We can measure with using of a goniometer, that is known as a contact goniometer. It was invented in 1780 by the Karangot. By the Karangot, you see here that is a goniometer. This one it is a goniometer, and it is, you see, it's a, let's see here, this, it has a measurements. So see here it has a measurements, and it is a movable, and it is a mobile. But how we can find out that? Just you see here, if you are putting the crystal here, you if you are putting the crystal, and the plane of or the face of a crystal angle we are find out here. So here the goniometer you can arrange parallel to this surface of this plane of this scale. It is a movable arm. You can arrange along this face, and the needle, it is showing the direction and angle. Here we can say yes, it has a 40 degrees of angle. We can say with using of this side of this face, the face of angle we can measure. We can measure. So for this purpose, the goniometer it is useful to us. So it is no the reflecting of a goniometer. There is no need to you in a detailed study of that. Okay, now we will go into the crystal indices. Yeah, here we see the crystal parameters. The crystal parameters, how we can define that? It is known as a crystal phase cut along the crystallographic axis of the phase. How? I'll show you that. You see here, the O, it's a midpoint of this one, and here, yeah, OA, OB, OC are the crystallographic axis which are origin from this one. This is a crystal. If you feel triangles, triangle formation of a crystal, this is a midpoint of this crystal, and the axes, these lines are known as the axis, crystal axis, OC and OA, OB. These are the basic crystal axes. OA, OB, and OC are the crystal axes which are origin from this one. Yeah, now it is in intercept OA, OB, OC, the crystallographic axis, the ratios OB, OA, OS, it is known as a ABC. Whereas, and again, uh, this is the one side of face. This is one face. This is one face, and this is one face. OCA, this is one face. OAB, this is one face, and OBC, this is one face. Now the imaginary lines, that means the outside, the outside of a faces where they are intersecting. Just we can imagine between this line. Here it is again the generating OF. Okay, OF, OD, and OE. Just you see here. See here. Uh, D, E, F are the imagine line which are passing through this line. Which are passing through this line, and it is indicating. It is indicating to the standard phase. Standard phase. You see, this is AF, AF, and CE, BD. This BD. These lines and it is a reference to the original one. D, E, F. You see triangle. This triangle, this triangle. It is indicating the. It is similar to the A, B, C capital numbers of. Okay, from this one here, we see the origin of the axis OA small and OB small axis, and OC small c. These small letters are indicating the axes. Axes. So here the crystallographic axes are generating, and which are travel through the solid angle. Through the solid angle. This is the angle. This is the solid angle or edge. In other term, we'll call edge. Uh, and corner also. This is edge and corner. Through two or three edges are making as or creating as a corner. These axes are generating from the O center point of this um, crystal, and which are passing through these corners. Through these corners, one it is A, and second one it is B, and third one it is C axis. These small letters are indicating as a axis. So here the faces A, B, C are connecting to here uh, one by one, two by one, one by two, one by one. One by one means complete. Here the corner here it is there. It is passing through this one. Complete. It is covering. It is covering complete line. So one by one, and second one it is intersecting the two lines. The B it is intersecting the two lines. This one and this one. Two lines. So 1 by 2, so 2 by 1, and the C it is intersecting only half here. This is intersecting, it is only half. So that is the reason it is 1 by 2. So here the crystallographic origin A, B, C are the crystallographic axes. These small A, B, C are the crystallographic axes. And through where it was origin at a O place. At a O place. You see here these lines. These lines. The connector lines are it is creating as a face. And the two faces will be joining at one on a straight line. It is known as a edge. This is edge. Two or three edge lines are creating the corners. It is a corners. From this is the origin point of O, the line is traveling through this corners. It is known as a axis. It is known as an axis based on the traveling and the cutting or intersecting of these edges. According to that, these are all the imaginary lines only. According to that, we will define the, or we will give the axes. It is intersecting one, or it is intersecting the two, or it is intersecting the three. According to that, we will give numbers. So here parameter system vices we will give. Actually here the vice parameter was introduced by the Christian Samuel Weiss. He was the greatest familiar scientist in the crystallographic axis. He was defined in 1818, which provide an approximate indication of phase orientation with respect to of crystallographic axis, and was used as a symbol of every phase. So those symbols are known as the indices we will call here. Let's see. The Weiss symbol and Miller symbol will call Miller symbol also Miller index according to that. You see, suppose if you're imagining this is one crystal, it's one crystal. Just you can imagine that one crystal, and through this crystal, you see here maybe this is one line and this is one line. If you're joining here one line and there one line, if you're imagining now this is one prismatic structure, we'll get it, and the origin of axis from this one is traveling through space and the horizontal and slant this the axis you see here. Can you imagine just these are all the lines, imagine lines. So here if it is a C, if it is a C and this one A and B, the C axis is intersecting the two axes A and B, so that 0 0 1 because of A it is equal to 0 and B is equal to 0, because of it is not axis, it is not intersecting, but C only intersecting, it has a long distance. So according to that given numbers 0 0 1 and B, this one, it is intersecting only one here also, so that 0 1 B and final one it is a 1 0 0 and it's also intersecting only one, so that we'll give A is equal to 1 and B is equal to 0, C is equal to 0, 1 0 0. So here the index system of the Miller indices were introduced by the W. Wellhel in 1829 and later by the W. H. Miller. In the system of notation, indices are used. The indices are the reciprocal of parameters. So the indices we'll write in the order of A, B, C. The letters it is indicating in A, B, C. And just you see here. Yeah. There are some symbols are given here to A, B, and infinitive C. The reciprocals of the parameters will be maybe if it is 1 by 2 and B is equal to 1 by 1. It is intersecting 1 and A it is intersecting 2 axes. So 1 by 2 and B and C it is infinitive. So that it's given 0 for that. Oh, this is the I mean, these are all the types of indices based on the formation of the different crystal, and the symbols it is indicating the phases. The symbols which are indicating these phases of a crystal. Example, the phase ABC unit if you see ABC and the reciprocals A by 1 A is equal to 1, B is equal to 1, C1 is equal to 1, C is equal to 1. So that's 1 by 1 and uh, 1 by 1. The Miller is all same 1 1 1. It's showing 1 1 1. but there is a differentiation based on the rotating of a crystals. So the Miller symbol, suppose if it is a one by one, and the axis it's a passing, maybe it is a through the single axis, it is a passing through the two edges, so that it is showing the two, and B it is passing through only one, and C it is passing the four. So that is so in a Miller symbol we will show that is 2 1 4. The Okay, what we have seen the symbols like 0 0 1 1 0 1, or sometimes maybe we see 3 1 also. Depend on their crystal faces, we have give symbols based on the arrangement of chemical elements. So here the symbols, or it is known as a index. Sometimes maybe we see those names like a cube 4 faces and octahedron 8 faces. Uh, Dodecahedron, it has 12 faces, and sometimes maybe trapezium also. Depend look like it is a trapezium. So that is the reason we will call that it's a trapeziahedron, and prism type structures and pyramid and dome type structures also we see according to that. The index will be given. Some crystallographic access in a posture, and sometimes we see it is in a two nature also. So depending on the formation of minerals, you see here, the side cube side faces and face symbols also given here in the question as a negative mode. Negative mode. Sorry, it is a signal problem. I'm getting signal problem here. You can see here the axis. Almost all the angles we see here, it is almost all 90 degrees. Oh, 90 degrees. Maybe it is A is equal to B is equal to C. The inclination of an angle, or the intersecting of an angle, we will call that is a we will call maybe that is alpha, beta, and gamma. Sorry, I don't want to show this one. Yeah. Yeah, previous feature what we have seen, A is equal to B is equal to C, it is equal to 90 degrees. And as well as here A it is equal to alpha, B is equal to gamma, and C is equal to, sorry, B is equal to beta, and C is equal to gamma, it is equal to 90 degrees there. And as well as here it is showing the positive and negative indices, negative indices. So here in negative and positive indices according to their intersection of different axes. So according to that, which are travel from A to B, and as well as B to A, and A to C, and C to A, according to that, we'll give indices in positive and negative nature. Okay, here crystal forms. Yeah, you see here open forms and closed forms. There are two types of forms we see. In a closed form, suppose example, if you see the assemblies of faces, which can enclose the volume of a space, sometimes maybe see in a cube, and it has six faces, or sometimes maybe we see it is a rhomboid decahedron. It has the Miller index almost 110, which is formed in a solid. It's a closed form. But whereas in a open system, here at least minimum two to few or faces are enclosed. The space it will be completely enclosed based on the crystal axis. They do not adequate the number of faces to do so, and the result of they occur in a combination of such like a zircon in a pyramid and prism forms. So combinations of depend on their combinations of faces. Sometimes we see triangular faces. In zircon, we see the triangular faces, or see these triangular faces. This one, two, and that side, and this side. 4 and 4, 8. The top one it has a 4, and the bottom it is also having the 4 plus 4. So the side here you see 1, 2, 3, 4. That side. So four faces it has. We'll give the name as per that, depend on their faces, number of faces. Example for you see a tetrahedron. The tetrahedron it has four faces, and shape of faces also depend on that. Pentagon, geometric formation, it is pentagon. And one more thing, it is arrangement of faces based on three. One it is the number of faces, and second one it is the shape of faces. Third one is arrangement of faces. According to that, we will give the names. So here, one more thing, it is the center of a crystal also. Here, the center of a crystal point, centrally it is coincided, and it is located mid of crystal. Suppose here, and here. There are two centers are there, and the axis will travel through this one, through this one. So now it is coincide the center of gravity of a crystal. It is maintained the gravity of a crystal. Suppose maybe here, almost all the axes travel through this one. So this point it is known as the center of a crystal. You see here four faces between these four faces, and the top eight faces between this. The center it has a face from this one. Here all the axis will travel through this one. Here is showing the some common forms. One it is monohedron. It is known as a pedion, and second one it is a two faces. It has. It is known as a pinacoid. Third one it is a prism. This one. This is. It's a pinacoid, bipinacoid, and fourth one is a pyramid. It is a prism, and fourth one is pyramid, like a dome structure on top. This. Yeah, again, dome structure it is also there. There is a this one, and sphenoid. This is known as a sphenoid structure. Rhombohedron. It is known as a rhombohedron. This one. These all the different formations are there. different forms what we will see, and I'll explain the next class about this. I'm stopping here. Okay, if you have any doubt, I have given number in the last class to Mr. Kumar, and you contact to him, and you take a number from him, and you contact me. Thank you.